Before we get into looking at the chain rule for composite functions, just a reminder that we looked at how the gradient can be written as the rise over the run being the change in x and the rise being the change in y. And if we take this distance between the 2 points and make it go smaller and smaller, we get dy dx. dy dx is just numbers, so that could be like 16 over 4, and if you bring the points closer and closer together, 8 over 2, then 4 over 1, until the point you have has a gradient of 4. So with that in mind, if I've got this function g, and that can be 3x plus 2, and that function is inside another function f, which can be all to the power of 4, then we've got the function 3x plus 2 all to the power of 4, which is a composite function, which is f is a function of g and g is a function of x. Now how do we differentiate this? We could expand it all by writing all the brackets out, and you get this, something huge, and then you could say, well, that's your function f of x. Now just differentiate with respect to x and you get the other, just take forever. We don't want to do that. So what we could do is say, here's our df dx. Remember, these are just numbers. So I could write that as df dx times the number 1, which could be written as some meaningful numbers like 42 divided by 42, that's just 1. If I wanted to, these are fractions, so I could rearrange them. I could make it df over a number, just rules of fractions. Now if df and dx are both numbers, then dg is also a number. Let's put that in here instead. So df dx could be written as df dx times dg dg. That doesn't change the equation at all. But if we rearrange it a little bit, df dx could be df dg times dg dx. And this is what we're going to call the chain rule. So if we go back to our original composite function, f, which is a function of g, which is a function of x, and we'll write up our chain rule again, then the function g is just this bit inside the brackets. So if I differentiate g with respect to x, I'll just get 3. And f is the outer function, which is in green. So that's everything inside the brackets to the power of 4. So that's f is a function of not x but of g. So f is equal to g to the power of 4. df dg is therefore 4g to the power of 3. So df dx equals df dg, which is 4g to the power of 3, times dg dx, which is times 3. And now that we've done the work, we could just change g and substitute in what g was, which is 3x plus 2, and simplify a little bit. The 4 times the 3 becomes 12. So without expanding, we've worked out the derivative of this composite function. Here's another example. F is a function of x. We'll call g the inside function, which is everything inside the brackets, and f is the function of g, so that's what's happening outside the brackets in this case. So the outer function is f and the inner function is g. So our chain rule says df dx. To differentiate f with respect to x means we differentiate f with respect to g, which is 65 g to the power of 4, and then we multiply that by the derivative of g with respect to x. So that is 6x squared plus 3. Now we'll just write out our chain rule. And now that we've done the work, we'll just change, we'll substitute in the function of g, and we're done. We could simplify, but normally we won't be doing this for just polynomials, so it wouldn't be necessary.